Hello everyone, welcome to our thesis end of semester presentation. Our thesis is titled Activity Classification. We're supervised by Dr. Cherif Salama and Dr. Mohamed Moustafa. We're a team of four. We're Diaa, Alaa, Hany, and Ramez. Here is our outline. We're first going to provide a recap, and then we're going to discuss the datasets used, and then Openpose expert, which is one of the experts we're using. And then we're going to discuss the architectures and our progress on them, and then our future plans, and lastly, the discussion. In essence, our project is concerned with human activity classification through images. The model would take an image and should be able to determine the activity taking place in the image. We're proposing a hierarchical approach to solve the problem, which would divide the problem space into sub-problem spaces. We're also utilizing multiple experts to specialize in different sub-problems. The division of the problem itself and the problem space would allow us to impose domain knowledge on the neural networks. In order to train our model, we'll be using the Boston University 101 Actions dataset. Going back in time, this is the very first visual representation of the architecture we proposed. The architecture came almost naturally, guided by the available datasets and models we first explored. Essentially, this architecture shows how we plan to obtain semantic domain-specific features from experts like a human parser and joins annotator and integrate them with hierarchical experts activated by a pre-classifier. We intended to make the problem simpler for classifiers by providing them with helpful semantic features. After that, the images pass through a pre-classifier, another highly accurate classifier that is trained to detect only main categories of activities, so that we cut the problem space into many small subspaces. Every image is passed into only one subspace classifier that further classifies the image into a final, finely grained activity label. Of course, this pipeline was only tentative and intuitive. It was redesigned after many rounds of testing and experimenting, and we ended up with different but isomorphic architectures on which we'll go through in detail in the rest of this presentation. So, what's the value of our proposed project, and how does it add to the existing literature? First, this solution could potentially improve on the state-of-the-art solutions on the same dataset. It was not tried before to combine sub-features from domain-specific knowledge for the task of human activity classification. Secondly, explainability is a key distinction between our project and what's in the literature. The solution produces intermediate features that could help explain the prediction of the model rather than having an opaque end-to-end implementation. Which brings us to modularity. Since experts do not need to reside on the same machine, we could delegate some computation on edge devices by pushing some light experts on the edge, for example. This could potentially provide a privacy-preserving solution, since we do not necessarily need to share the images to the main network at the server side. We just need the outputs of the experts. And lastly, the solution idea itself of human activity classification, regardless of the architecture that we're gonna use, can be used for safety analytics by detecting certain activities from footages of security cameras, for instance.
Regarding the datasets, we initially planned to use the Max Planck Institute for Informatics Human Pose Estimation dataset for its multi-labeling for human activities. It had 20 main classes and around 410 subclasses. An example of a class and its corresponding subclass would be sports and football, respectively. However, the dataset was not designed for activity recognition, although it contained labels for activities. So when we downloaded the dataset and started exploring with it, we found out that many activity labels were missing. We contacted the authors of the dataset, and they told us that the left-out information was intentional, for privacy reasons. This deemed the dataset unusable for multi-label activity recognition. This is because there was a large number of missing activity labels, leading to an insufficient number of images for training. In some classes, we had under 10 images, for example. So we had to look for another dataset to fulfill the task of activity classification. We found another dataset, Boston University Actions, which comes in multiple variations: BU11, BU11 unfiltered, and BU203 unfiltered. In our project, we will be using BU11, which has around 24,000 labeled images, having an average of 235 images per class. From the name, the dataset has 101 classes. Examples of classes would be biking, archery, drumming, and brushing teeth. The dataset inherently has the hierarchical labeling, having each class belonging to a superclass. Superclasses here include human-to-human interaction, human-to-object interaction, playing musical instruments, and sports. Such division is merely logical and not embedded in the label dataset. This basically means that an image would have a label for its activity. For example, it would say that the image is biking, but it wouldn't say the biking belongs to the sports superclass. So, such multi-level labeling had to be done manually in our code, abiding by Boston University logical division of this dataset. What we can do here is find more activity-specific datasets to increase the number of training images whenever the number of images in a class is relatively low. So, we'd see the poorly performing classes, and adding training examples, in the case the number is limited, would be an option here. In our architectures, we are going to use multiple experts that provide semantic features relevant to our problem. Openpose is one of the experts we experimented with. Its performance is benchmarked on the state-of-the-art datasets, such as Max Planck Institute of Informatics Human Pose Estimation Dataset, and COCO. It is a real-time multi-person system to jointly detect human body, hand, facial info key points. In total, 135 key points are detected on every image. In Openpose's 2D functionality, it detects multiple people in the same image and provides features for each of them. Those features per person are up to 25 body and/or foot key points, 21 key points per hand, and 70 key points to represent the face. It also does 3D real-time single-person key point detection, but we're only using the 2D functionality for now. Openpose also provides a calibration toolbox, which provides estimation of distortion, intrinsic and extrinsic camera parameters. For input, it takes images, video, and camera raw outputs. The output of Openpose comes in two main formats: images rendered with annotated key points on top of the image, and key point vectors saved in textual formats such as JSON, XML, and YAML. In our project, we aim to produce a publishable research paper in which we'll explain our architectures as well as benchmark the results. In order to be able to do such a comparison, we devised 4 architectures, one of which is a baseline model. We will be developing the 4 architectures and then compare the different performance of each. Hypothetically, as we progress in the architectures, the accuracy is expected to increase, with architecture 4 having the best performance. These 4 architectures will be explained in detail in the following few slides. The first architecture we developed is an end-to-end model that utilizes a VGG11 model. VGG stands for Visual Geometry Group, and it's a state-of-the-art off-the-shelf image classification model. Essentially, the VGG model can be divided into 2 main parts. Number 1, a feature extractor, which consists of a set of convolutional layers. And number 2, a classifier, which consists of 3 fully connected layers. We will be considering the VGG model as our baseline, which we will be comparing the other architectures with. In all our experiments, we replace the last fully connected layer by another one that has an equal number of nodes to the number of classes we have. We experimented with 3 different training configurations of this model, and these can be found in the slide. We realized from the first experiment that starting from randomly initialized weights is probably not the best approach, and instead we should use the pre-trained weights of VGG11 as a starting point. The second and third experiments indicate that retraining the whole network instead of just the classifier can reach a higher accuracy, yet the increase in the accuracy is minimal when compared to the cost of training the network. In later experiments, we'll need to freeze the feature extractor net to make it common to multiple classifiers at the same time.
With all the variations, our baseline model was able to reach an accuracy of 81.53%. After experimenting with architecture 1, we moved to architecture 2, where we divide the problem space. Instead of trying to classify an image out of 101 classes directly, we introduced a super classifier, which classifies each image into 1 out of 5 categories. These 5 categories are sports, human-human interaction, playing musical instruments, body motion only, and human-object interaction. Then, based on the category of the image, we'll be passing the features of the image to a specialized classifier that's trained on this category only. Ideally, we would have a feature extractor for each classifier. However, due to memory bounds, we weren't able to fit 6 feature extractors in the memory. Instead, we decided to use the same VGG feature extractor for all our classifiers. So the flow of an image in our model is the following. We extract the features using the VGG11 feature extractor. We pass these features to a super classifier that predicts a category for each image, and based on the category, the features are passed to a specific subclassifier which uses these features to classify the activity of the image. Unfortunately, the results of this architecture were not very promising. The accuracies of all the classifiers ranged between 81% and 89.6%, and the combined hierarchical pipeline was not able to reach an accuracy higher than 74%. The largest problem with this architecture is that the super classifier has an accuracy of 88.6%. This is problematic because of the nested nature of the architecture, and as a result, if the super classifier fails to classify the category, the outcome will be incorrect regardless of how accurate the subclassifiers are.
In the second half of the semester, we focused on Architecture 3, where we experimented with adding experts to the feature extraction stage of the pipeline. This was our initial depiction of this stage, where we have the normal VGG feature extractor accompanied by other feature extractor experts like pose estimator, one like Openpose that we discussed earlier, a human parser, a clothes extractor or a classifier, maybe a VGG on the background to extract features from the background itself, and so on. For this stage, we have only experimented with adding the Openpose expert, introducing features of joints, hand, and feet to the extracted features from VGG. And to combine these features together, we have 3 different approaches that are to be discussed in the next slides. In the first approach, we experimented with adding the pose features of the image itself before feeding it to the VGG extractor. This effectively does not increase the feature space, but rather adds information to the image itself that is uniform across all images. The intuition behind that was that certain sports have very specific poses that could easily be extracted visually, and that human-human interaction could be easily identified by 2 overlapping skeletons of joints in the image. The pipeline of this experiment was as follows. The image is processed and rendered by Openpose pose estimator. The output images would be fed to the VGG extractor, and then the pipeline would continue normally as in previous architectures. As we will see in the results section, this approach in fact produced less accurate predictions. This could be attributed to multiple things. For example, the annotations themselves could obstruct information that was relevant in the image before, and therefore confusing the model. An example of such information could be the facial features or the facial expression of the person in the image. The second approach, however, was very straightforward. The task was to concatenate the 2 feature sets extracted from both experts separately before feeding them to the classifier. By limiting the number of people in every image extracted from the Openpose estimator to 2 people, we have 2 sets of key point data outputted from the expert. And whenever there were no people in the image or less than 2 people in the image, we would default these feature vectors to zeros. While this architecture looks very promising, with no loss in the previous features that produced good results, and additional features that are possibly relevant and useful, it still resulted in less accurate predictions. And we are not exactly sure why. But possible problems could be due to losing all the pre-trained weights in the classifier. Since we changed its input, we are no longer able to retain the pre-trained weights from VGG in the classifier and fine-tuning on them as we did before. Another problem could be because the pose features themselves are not similar or compatible to the features that are extracted from VGG, and so they were rather confusing than insightful to the classifier. So we tried to push the introduction of these features further into the pipeline, into the classifier, which leads us to the third approach. The VGG classifier stage, as introduced earlier, mainly has 3 fully connected layers. In this approach, we introduce the Openpose features after the first fully connected layer. The first fully connected layer is the one that reduces the feature space of VGG features from 25K to around only 4K features. This way, we kept the pre-trained weights of the first layer, and we added the outputs of the Openpose to a more concise feature space that was then fed normally to the rest of the model. This approach actually very recently resulted in the first improvement over the baseline. We're still investigating how this approach achieved such results and the reasons behind its success. However, it consistently provided better results, even when we tried it with pre-classifiers and subclassifiers from previous architectures. In this slide, you can see the summary of the results of Architecture 3 in terms of accuracy. We can see that the third approach performed mostly better than the other two, especially in the end-to-end classifier model. The second approach still needs further experimentation with all other experts, but the results obtained from the end-to-end experiments made us delegate these experiments to later. In this slide, you can see a summary of our results from all architectures in terms of accuracies. We can see that the third approach in the third architecture has the best overall performance, beating the baseline, especially in the end-to-end. And when this architecture was applied to experts that are different from the end-to-end, so the superclass classifier, the body motion, and so on, it performed similar to those experts in Architecture 2, sometimes better, like in the body motion, the human-object interaction, and in the sports, sometimes worse, like in the superclass classifier and the human-human interaction, and tying in the playing musical instruments category. In the next period, we'll be concentrating on Architecture 4, which is a combination of all the architectures that we encountered so far. We will try to incorporate multiple experts in the feature extraction stage, and after fixing and improving the architecture number 2, which divides the problem space using the superclass classifier and the subclassifiers, we will try to incorporate that architecture into Architecture 3 as well, and improve the overall accuracy to produce Architecture 4, as you can see in this image.
Given our current progress this semester, we have many future plans that essentially serve our purpose, achieving an explainable hierarchical model that solves the activity classification problem with a higher accuracy than the end-to-end models. First, we'll investigate the possibility of adding a heuristic pre-classifier in our architectures. After all, we need the heuristic pre-classifier to solve a very simple problem, rather than dealing with activity images directly. We might use a collaboration of multiple state-of-the-art object detection models that will provide us with object counts. Based on specific criteria and heuristic conditions, we could infer the superclasses from them. Secondly, recalling our architectures 2 to 4, we had a VGG component that does feature extraction on images alongside other experts. This essentially defies our purpose of achieving an explainable model, since VGG features are not semantically driven. So we might remove the VGG feature extraction component, add more feature extraction experts that provide a semantic-rich feature vector space for the problem, and investigate how such a combination performs. As for our Architecture 4, once we're done with Architectures 2 and 3, we'll have our experts and subclassifiers architecture ready to be integrated. We'll use the best pre-classifier we achieved, either end-to-end or heuristic. We'll also use the best feature vector combination, and we're gonna experiment with the model. And then comes our hyperparameter tuning stage, which is going to be applied on all our architectures. Once we're done with all our architectures, we'll benchmark our architecture's performance against each other. Once we're done with benchmarking, fine-tuning the architectures, and producing significantly better results than the end-to-end model, we'll start writing our first research paper manuscript. For that, we'll look for journals publishing relevant papers in our domain and find out the best outline for our manuscript to be based on.